Okay, so let's continue with the solution approach that we can use actually to prevent many processes to be in the critical region. Okay, so we have said that we have to structure a program or the processes, concurrent processes, in this manner. The concurrent many processes should be structured in this manner. So before the critical section, they should have an entry section. After the critical section, they will exit the section. Okay. For example, here they may try to get a lock, enter the critical section, and then release the lock. Okay. If you are using locks to control access to the critical section. Okay. Here, this exit section is nothing to do with the exit system call. Okay. This is called you are leaving the critical section. Okay. So there may be many solutions that are structured in this manner. So what do you do here? Okay, determines the solution. So you can propose many different solutions, each doing something different. It is here and there. Okay. So whatever the solution is, actually we expect some properties from those solutions, so that they are good enough. Okay. These are the three properties that we expect from a solution, critical section problem solution. One is the mutual exclusion, meaning that if a process PI is executing in its critical section, then no other processes can be executing in their critical sections. This is the mutual exclusion, meaning that if I am a process that is now entering the critical section and entered the critical section and executing the critical section now, that means I am touching the global variable or shared data. I should exclude, or the solution should exclude, all the other processes to enter and execute the same critical section code. The critical section code may be different, but a code that is accessing this same shared data. Okay, so that only one process may be in the critical section code. Okay, so this is mutual exclusion. The processes are excluding each other. So if one of them is executing the critical section code, the other processes cannot execute the critical section code during this time. After that process has finished executing the critical section code, another process can go and execute critical section code. Okay, this is the mutual exclusion property. A solution should enforce this, should provide this. Okay, it should allow only one process to be in the critical section. Another is the progress, meaning that if there are several processes waiting to enter the critical section, okay, then the selection of the process that will enter the critical section next cannot postpone indefinitely. Sooner or later, one process should be going and entering the critical section. Okay, if there are processes that are waiting to enter the critical section, sooner or later, one of them should be able to enter the critical section. Okay, so that we make some progress. You can have, of course, a solution which is actually preventing all processes from entering the critical section forever. So nobody is in the critical section, so mutual exclusion is provided. Okay, there is no danger of race conditions, but this is not a solution that is good because it is not making any progress, right? So this is the progress property. And another issue is here. If I am a process that would like to share data with some other process, okay? If I am entering the critical section, executing the critical section code, the other process should not be executing critical section code. But if I am executing something else in my remainder section, not touching to the global variable, okay, then the other process should be able to enter the critical section. In other words, if I am executing in my remainder section, I should not prevent another process to enter the critical section. Okay, I can only prevent if I also want to access the critical section, execute the critical section code. Then I can prevent the other one to execute the critical section code. But if I am in the remainder section, nothing to do with the shared variables and so on, then I should not prevent some process that would like and go and execute the critical section code. Okay. Another third property is the bounded waiting. There has to be a bound, okay, on the number of times that other processes are allowed to enter their critical sections after a process has made a request to enter its critical section and before that request is granted. Okay, for example, this is the critical section code. I would like to execute that. Another process would like to execute that as well. Assume that process is allowed to run now. That is running, okay? I am waiting. That process may run for a while and then exit the critical section and then may come back and enter the critical section again, okay? This may be the case. And then go and come back again, enter the critical section, execute it. During this time, I may be still waiting, okay? There should be a bound on such repetitions, okay? For example, the solution may allow the other process to do that at most 3 times, but there should be a bound so that at the end, I will have a chance to enter the critical section and execute critical section code, okay? So that means there should be a bound on the amount of time that I will wait another process that's entering the critical section, leaving it, entering it, leaving it, and so on. There should be a bound that I wait for the other process. Most of the time, to be fair, that other process should be allowed only once. And then I should be allowed to enter the critical section. And then that can be allowed again, and so on. But in a row, twice in a row, that process should not be allowed in most of the cases, okay? So this is bounded waiting. There should be a bound on the amount of time that I should wait to enter the critical section. Another process, okay, there should be a bound for that waiting time. Is clear? And we are not making any assumption about the speed of the processes. We assume that they are executing at non-zero speeds, okay, but we don't make any assumption about the speed of the process. We don't say that this process will run faster than that one and so on. We don't make any assumptions, okay? So now let's look to some solutions, okay? Now let's look to some solutions. One solution is Peterson Solution, okay? This is a software solution. This is just programming at the application, okay? And you obtain the solution. You don't require any support from the hardware, kernel, and so on. Without the kernel support, without the hardware support, you can actually program your programs in the way that this solution suggests and have this problem solved, okay? Race conditions avoided, okay? But this solution is a software solution, pure software solution, and it only works for just two processes, okay? If there are two processes that would like to share a data item, okay, then their activities can be coordinated using this solution, okay? But if there are many processes that would like to share the same global variable, then this process will not work, okay? It is not actually solving the critical section problem for more than two processes. And it also makes an assumption. It assumes that some machine instructions like load, store are executed atomically, not the high-level statements, the machine instructions, okay? It assumes that they are executed atomically. That means when a process is executing the load machine instruction, it cannot be suspended before it finished executing that instruction, okay? It can be suspended, of course, before it starts the new instruction execution. Between two instructions, it can be suspended, but in the middle of an instruction, single machine instruction execution, it cannot be suspended, okay? So this is the assumption that it makes. So now what is the solution? Before discussing the solution, actually, we can think of a little bit how we can provide the solution. How can you enforce that only one process is executing the critical section code? Can you suggest a way? A possible way could be something like that. You can use another variable, let's say log or something like that, integer variable. Set it to 0, right, initially. Set it to 1. A process that would like to enter the critical section may check the value. If it is 1, it enters. If it is 0, that means somebody has actually decremented it. It will not enter the critical section. So whenever you check a value, if it is 1, you decrement it to 0 and enter the critical section. In this way, if the log is 1 at the time that you have checked, that means you can go ahead and enter critical section. If the log is 0, that means somebody has actually set it to 0, so you should wait, okay? If this is the solution, do you think it will work? Yes. Exactly. So since that log integer variable is also shared variable, okay, you will experience the same problem, okay? You will experience. So just using a single variable without another protection and so on is not enough, okay? So this Peterson solution is now using two variables. One is, both of them are shared variables, okay? These two variables are these. One integer variable called turn. The other is an array of two entries. And the entry type is Boolean, okay? So you can store two Boolean values into that array. The array name is flag, okay? So here, in this array actually, there are two processes. You have one entry per process, okay? Process 0 is using, for example, flag 0. Process 1 may be using flag 1, okay? Flag array indicates that the entry for a process indicates that that process would like to enter the critical region. If you would like to enter the critical region, then you set your flag to true, okay? Otherwise, you set it to false. That means after you exit your critical section, you set your flag corresponding entry in the array to false, okay? So flag indicates whether the process would like to enter the critical region or not, whether it is interested to execute critical region code or not, okay? So this is the use of the flag. It indicates this. And the turn indicates whose turn it is. There are two processes. Is it that process turn or that process turn, okay? So it can have value 0 or 1. If it is 0, that means process 0 can execute. If it is 1, that means process 1 can execute, okay? So the variable turn indicates whose turn it is to enter the critical region, and the flag array is used to indicate if a process is ready to enter the critical section. If flag is true, implies that process Pi is ready. If flag I, where I can be 0 or 1, assume the processes are identified with 0 or 1, okay? If flag I is true, implies that the process Pi is ready to enter the critical section, is ready to, okay, wants to enter the critical section, okay? So now, there are two processes that would like to access a shared data item in their critical regions, okay? And then the processes can be structured in this manner. From time to time, they execute critical section code. We are just showing critical section here, but it's actually a piece of code that is touching to some global variable or shared memory variable, okay, maybe manipulating, updating that. And then they execute in their remainder sections where they do not touch to shared data, okay? So one process may be executing this for a while, okay, maybe all the time. Another process will be doing the similar thing. From time to time, it will go and access the shared data, and then it will do something else, and then it will come back and access the shared data, execute critical region code, okay? So assume two processes are executing code, a program that looks like the following. Each process may execute a different program, but the structure of those programs are actually modeled with this simple program here, okay? An endless while loop where we execute critical section code from time to time, and then we also execute remainder section code, okay? In the critical section, we are touching to a shared variable, all right? So these programs, two programs are executing a code similar to this, okay? So now this algorithm will do what? It will insert actually an entry section code, okay? If you want to ensure that only one process is now executing in the critical section, you have to now put some code which is called entry section that will prevent other process to enter the critical section if one process is executing here. This piece of code here will allow only one process to be here, okay? So we will examine that piece of code. And also after the critical section, we insert exit section, okay? That is, for example, in a simple example, it's just setting the flag value to false, okay? So two processes, each will be having this structure, okay? Two processes, whenever they would like to enter the critical section, they have to execute this code, okay? And then execute critical section code, and then they have to execute this piece of code. You can think that this program here, this simple program, is executed by two processes, for example, okay? So now let's look how this is solving. So a process that would like to enter the critical section is doing what in the entry section? It sets its flag to true. This is logical, right? So you indicate that you want to enter the critical section. You are interested in entering the critical section. You set your flag. Assume this is the process I. Okay? I can be 0 or 1. Okay? Process I. The other process is process J. Okay? If I is 0, J should be 1. If I is 1, J should be 0, for example. Okay? Assume we are identifying the processes in this manner. Two processes, I and J. 0 or 1 or 1 or 0. Okay? So if process I would like to enter the critical section, it first sets its flag to true. And then it becomes nice to the other process and yield the turn to the other process. It sets the turn to J, the ID of the other process, okay? For example, if I is 0, J is 1, okay? So you set flag 0 to true and you set turn to 1, for example, okay? And then it executes this while loop here, whose condition is this. That means loop around as long as flag J is true and turn is equal to J. So assume I am process I and that is process J, okay? So I am executing this piece of code. I set my flag to true. I set turn to be equal to that process's ID. and I am now checking these conditions. As long as flag J is true, as long as the other process would like to enter the critical region, and turn is the other process's turn, that means I have to loop, wait, busy wait, okay? I cannot go and execute the critical section. So this while statement here will cause me to stop, busy loop, okay? And not enter the critical section. I am not stopping, I am looping, but it prevents me to enter the critical section. Let's look, for example, while I am doing that, assume the other process, since its flag is true, okay? If the other process is flag true, then I am looping around. If the other process's flag is false, assume, what will happen then? This condition will be immediately false, right? If the other process did not set its flag to false, that means the other process would like to enter the critical section. It is actually executing in its remainder section. So it is not in the critical section definitely, right? And it doesn't want to enter the critical section at the moment. So its flag is false. That means even though I had set the turn to J, I have been nice to him, but actually he is not interested to enter the critical section. So this condition will be false for him, right? And I will be able to enter the critical section because I will be breaking the while loop immediately and going to the critical section. So I can go into the critical section then if the other guy is not interested to enter the critical section, or that is interested but turn is mine. If the turn is mine, or if the other process is not interested, then I can go and enter to my critical section, okay? So now let's look to this. So if I want to enter the critical section and the other process doesn't want to enter the critical section, then flag will be false, flag J will be false for the other process, so I will be entering the critical section, no problem, right? So this allows me to enter the critical section. Let's assume that while I am in the critical section, the other process would like to enter the critical section. So it starts executing a piece of code. It will set its flag to true. It will set turn to me, right? And then it will check this here. As long as my flag is true and turn is mine, okay, it will loop around, okay? So the other process will loop around. When I leave my critical section, what will happen? I will set flag to false. At that time, the process that was looping around, okay, we see that now the my flag has become false. So now that condition will be false for him, and it will be able to enter and execute the critical section code, okay? So here actually I show it, these two processes, and the code they are running side by side so that you can understand better, okay? Assume we have process 0 and process 1. So process 0 is executing this piece of code, process 1 is executing a similar piece of code. Their critical sections can be different, but they should access the same global variable or shared variable, okay? So each of them has the same entry section, okay? So when this process, for example, assume they nearly would like to enter the critical section at the same time. What happens? Let's look what happens at that time. So we are now looking whether this solution can enable two processes to be in the critical sections at the same time. It should not, but maybe it is doing that. Let's check it, okay? So if both of these processes would like to enter the critical section nearly at the same time, okay? So that means they are running this piece of code here concurrently. So they are each is setting its flag to true. Flag 0 is true, flag 1 is true. Each setting the turn to be the turn of other, okay? So this is setting the turn to 1, the other one is setting the turn to 0, right? And then they are just checking the flag value and turn value. So this is checking the flag and turn, the other's flag, and checking whether the turn is the other process turn, okay? And the other one is doing the same thing. It is checking the flag of this process and checking whether the turn is that process and so on. So as long as the flag of this process is true and turn is that process's turn, this should loop, okay? So then what can happen? So for both of these processes, the flag will be true, right? Since they indicate that they would like to enter the critical section. Flag will be true, flag 0 and flag 1 will be true, okay? They are setting their own flags. But here the turn variable here is shared variable. So this may be running this statement and setting to 1, but then this may be running and setting to turn to 0, okay? Whoever runs first and last, at the end we will see that turn is either 1 or 0. It cannot be both, right? Can it be both? Turn is a shared variable. Whether there happens a race condition while updating the turn or not, okay? No matter what happens, at the end, turn will have a value either 0 or 1, right? This is guaranteed. Then what will happen? If it is, when it will be 0, if this executes later than that one, then it will be 0. If this executes later, then it will be 1, okay? So whoever executes later will give the turn. Or whoever executes the turn actually first will have the turn to set to itself. So for example, if this had set to turn 1 and then that has set to turn to 0, that means as a result the turn will be zeros and this process will be able to enter the critical section because turn is equal to 1 condition here will be false. Okay, and turn is equal to 0 condition will be true, so this will loop around, flag is already true. So while this is looping around, this guy will see this condition to be false and it will be entering the critical section. It will not loop around, okay? So since turn is either 0 or 1, that means either this condition or that condition will be definitely, only one of them will be true, the other one will be false, okay? For the process for which this condition is false, that process will not loop around, it will be able to enter the critical section. So only one of the processes it will be false, okay? It cannot be false for both of the processes. If it has been false, both of the processes, then both processes would be able to enter the critical section. And this would not be a correct solution then. Since turn can be either 0 or 1, that means only for one process this condition can be true, and only that process will be able to enter the critical section. So that this solution provides mutual exclusion, yes.
What if you have n processes?
So this is not a solution designed for n processes, okay?
Just 2 processes?
Yes. So it's a solution that's designed for just 2 processes, okay? So this is actually a solution that provides mutual exclusion. Any questions here? And here, as you see, the flag array and the turn are shared variables. So what happens after a process executes the critical section? It simply sets its flag to false, so that another process that was looping here, waiting the flag of the other process to be false, will see it to be false, and it will be able to enter the critical section, okay? Any questions? So this actually provides mutual exclusion in this manner. So let's look, for example, what happens. Assume one process is now waiting here. One process is now waiting here, okay? And the other process is in the critical section. This process will be waiting here. Why? Because the flag of other is true and also the turn is 1, okay? So process 1, assume, is now executing in the critical section. So turn is 1 and flag of 1 is true. When it has finished executing, what can happen? So it will set its flags to false, right? But as soon as it finishes the critical section, there is no guarantee that this will be suspended and that will be run. This may continue running. This may continue running, right? So this was looping around here. This was looping around here in the CPU, and then process switch occurred to that process. So this is suspended at that while loop, right? This may happen. So this is running now in the critical section, and then it's exiting the critical section, setting its flag to false, but assume it is continuing running. This may happen, right? The kernel did not schedule the other process yet. So it can execute the critical section, and the critical section can be quite short. So it may immediately come back here and may want to enter the critical section again. So what will happen in this case? It will set its flag to true, but it will set the turn to 0, right? So then what will happen? So in this case, since it sets the flag to 0, so the turn to 0, so now this process will wait, will loop around. So this condition will be true, and flag 0 is already true, because this is around here in its execution, so it has set flag 0 to true. So now this process has to wait, and this process will be able to run and enter the critical section, okay? Any questions about this solution? So this is called Peterson Solution, okay? So as you see, it's pure software solution. You just insert this piece of code. You declare these shared variables, flag and turn, shared variables, and then you insert this piece of code in every concurrent process. These process 0, P0 and P1 can be two threads, then they can be global variables, or they can be two processes, then they have to be variables defined in the shared memory or in a file. Okay? Is it clear? But however, this is pure software solution. Many systems actually provide hardware support for critical section code as well. We will now see some hardware solutions or solutions that get some help from the hardware. This help is in terms of some machine instructions that are atomic, okay? More complex machine instructions. One solution can be actually just disabling the interrupts. In uniprocessor environment, you can do that. If you have a single processor in your system, okay, then whenever you would like to enter the critical section, okay, you can just disable the interrupts at this point and then enable the interrupts after the critical section. But this is not desirable. But assume you are allowed to do that. Then what will happen? When you disable the interrupts here, while you are in critical section, clock interrupt will not arrive. No interrupt will arrive to the CPU. Therefore, your execution in the CPU will not be suspended until you enable the interrupts again. So therefore, there can be nobody that can actually interleave or interrupt your execution of the critical section code. So you are safe, okay? So no context switch will occur and so on. Therefore, while you are touching to a shared variable, you are guaranteed that you will finish. And during this time, nobody will go and execute. And then when you are finished, you can enable the interrupts, after which clock interrupts may arrive and kernel code can execute again and maybe schedule another process. All right? In this way, disabling interrupts actually prevents the race conditions and so on, but you should not allow the user processes to disable the interrupts. It is not a desirable thing, but kernel code actually can disable the interrupts. As I said earlier, race conditions may also happen in the kernel code, not in the user code like here. Kernel may have to deal with the race conditions as well. For that, it may disable the interrupts in a unit processor environment. But for multiprocessor environment, disabling the interrupts will not work. Why? Because you are disabling the interrupts only for your processor. That means if you disable the interrupts, that means that that CPU will not get and process any more interrupts. That doesn't mean that other processors will not get interrupts, okay? So each processor has its own interrupt mechanism. So you are only disabling the interrupts here in this processor. So that means if I disable the interrupts here, okay, and start executing critical section code, another process that is running in another CPU, since the interrupts are not disabled there, okay, since we can have other processes executing and coming to here, okay, entering the critical section at the same time, so they can touch to the shared data even though you have disabled the interrupts. You are guaranteed your execution in that process will not be interrupted, but that doesn't mean that another process in another CPU cannot run. Another process can run in another CPU, it can have interrupts there and so on. So another process can run there and access the shared data while you are accessing the shared data, okay? So disabling the interrupts in multiprocess environments will not work. Some other solutions are required. So let's look to synchronization hardware solutions. The idea is actually using log variables, but not just as simple integers, okay? Or you can be using simple integers, but using some advanced machine instructions, more complex machine instructions, okay? As I said, as we discussed earlier, just using a simple integer value as a log variable may be the source of the race conditions itself, okay? If you are incrementing, decrementing that integer variable with ordinary instructions, then that integer variable can be the source of race conditions. So what we can have is hardware can provide actually extra and more complex machine instructions to avoid race conditions. And we will see now those instructions, okay? And the solution idea is this. The general structure of a solution will be something like that. If you have a program that has critical sections and remainder sections, you will first try to acquire a lock, meaning that you will, for example, set the lock to 1, to 0 or 1. If lock is 1, for example, that means you acquired that and nobody can get the lock. Okay, then you enter the critical section and execute that, and when you finished with the critical section, you release the lock, meaning that you set the lock value to 0, for example. Okay, again. So this is the general solution structure. So how can we implement this acquired lock and release lock sections? This is the question, and we will see the implementation of those sections with hardware instructions now. Okay, so modern hardware machines provide special atomic hardware instructions that are doing more than just, for example, moving a value from memory location to a register, or more than just incrementing a value. Okay, so two instructions we will discuss. One is the test memory word and set value instruction. We call it as test and set instruction. And the other instruction that we will discuss is swap contents of two memory words instruction, swap instruction. Okay. So let's look to the test and set instruction. Assume the hardware, the machine language for that hardware, or the machine instructions of that hardware includes this instruction as well. Besides move, besides increment, decrement, add, and so on, right? It includes such an instruction that's called test and set. Okay, it's a machine assembly instruction. Of course, if you would like to use that to program a solution, then you have to program in assembly. Okay, hence the entry section code should be programmed in assembly. Here, let's look to the definition of that machine instruction. We are providing the definition of that instruction in high-level language, in C. Of course, it's a machine instruction. Okay. But here we provide definition using a high-level language. So this is the definition. Test and set machine instruction definition. Okay. So it operates on a memory variable of Boolean type. Okay. Target. This can be, for example, representing your lock variable. Okay. So it can be lock, for example, but it's a Boolean variable. It can either store 0 or 1, true or false. Okay. So if you execute this instruction on that memory variable, this will be happening in the system, in the hardware. It will get the value of that memory variable into a register, for example, or okay, into a value, into another variable, RV, let's say, and then it will set the value. So assume we have that value in memory, okay, variable in memory. We read the value, and then we set the value to true, and then we return the value. So as a result, it is both reading the value into a register, and it's also setting the value. Normally, you would do this operation in two machine instructions, moving the value from a memory variable into register, and then setting the memory variable value to 1, for example, or true. They are normally implemented using two machine instructions. But now we have a single instruction that is doing that. So that instruction is just returning you the previous value and also setting the value of the target to true. So after you have executed such a machine instruction, what do you have in your hand? You have in your hand the previous value of that variable, target or lock, plus you have set the value of that lock or target to 1 as a side effect. Okay? So now you can use this machine instruction to program a solution for the critical section. So this is the solution actually. Okay? So what it is doing is, before the critical section, you insert this piece of code, okay, as the entry section. All right? In the entry section. So what is it doing? It is now a while statement, just calling or using this machine instruction test and set with lock memory variable. So what is the effect? It looks to the value of the lock. If it is 0, it breaks out of the value. That means lock is not set. You can get the lock and enter the critical section. Okay, lock is 0. It is not locked. The critical section is not 0. Lock is false. Okay. So, but as a side effect, atomically, while doing this check, it's also setting the value of the lock to 1. Okay. While you are checking this here, somebody else cannot do the check and set again. While you are checking the lock value, you are also setting to 1. Okay, so as a result, you see that it is 0, and you come here, but as a side effect, you also set the lock to 1. Okay, when you come to here, and just in the beginning of the critical section, all right, you already set the lock to 1. So somebody else who is now executing this piece of code to enter the critical section, okay, will do what? Will again use this machine instruction. They will look to the lock value, but they will now see the lock value to be what? To be 0 or 1. 1, right? So it's already set. So then, if the value of the lock is 1, that means the condition is 1. So such another process will just loop around, okay? And will not be allowed to enter the critical section. So there is no danger like this here. You look to the lock value, see it as 0, okay? But before you could actually set it to 1, a context switch happens and another process runs, sees the value as 0, and sets the lock value to 1 and enters the critical section. This cannot happen to here because checking the lock value and setting to 1 is done with a single machine instruction. That's invisible, okay? So you just see the value of the lock and see it as 0, and you cannot be interrupted during this time. You also set it to 1. You decided to go ahead, and you also set it the lock value to 1. After that, you can be interrupted. Your program has already decided to go to the critical section. It will return from the while loop, okay? It will break from the while loop. But during this time, it has also set the lock value. Even though you get now interrupted, suspended, another process that executes similar code here will see the lock value 1, and now it will loop around. It will not be able to enter the critical section, okay? So having such an indivisible operation, atomic operation, helps you with the solution, okay? So when you finish with the critical section, what will happen? You set the lock value to false again. So another process that was busy looping here, checking the lock value always and seeing it 1 and looping because of that, will now see in the next check, we now see the lock value to as what? As false or 0. So it will decide to break the while loop, but it will also set the lock to 1 as a side effect in one indivisible operation. And then it will be able to enter the critical section. Once it is in the critical section, or once it has decided to enter the critical section, it breaks the while loop. It has already set the lock also to 1, okay? Any questions here? We can actually code this in assembly like this, okay? So you can encode the entry section and exit section also in assembly. So here, TestAndSet, for example, can be a machine instruction that is reading the value of lock from memory into a register, and meanwhile setting the value of lock to 1. And then looking to register value, whether the lock value was 0 or 1, okay? So what this piece of code, assembly code, is doing is first executing this machine instruction, which is taking the lock value and putting into register. The lock value can be 0 or 1. You will check it later. You will look to the register, okay? Whether either 0 or 1, no matter what it is, as a result of this assembly instruction execution, this will be having a value what? 1 afterwards, okay? So now you check the value. If it was 0 before you execute this one, since the previous value of lock is stored in register, you have the previous value of the lock, right? The current value is 1 after you execute this machine instruction. So you now compare the register value into which you have stored the previous value of the lock. You compare the register value with 0. If it is equal to 0, that means the previous value of the lock was what? Was 0. That means lock was not acquired by somebody else. Lock is available. You can go ahead and execute your critical section code. That means you can return. So you are not jumping to here. All right? If this is not equal to 0, that means if this is equal to 0, sorry, that means you are not jumping. If this is not equal to 0, then you have to jump. Jump not equal instruction, okay? If register is 0, that means previous value of the lock before you execute this instruction was 0, that means nobody in the critical section. So you are not jumping to here, so you are returning. So after you return from that entry section, you can go and execute the critical section code. Okay, but as a side effect, you set the lock to 1. That's something that we want, right? If we want to enter the critical region, we want set the lock to 1 so that somebody else cannot enter the critical region. So assume now, consider another scenario. Assume the lock was 1. All right? So you execute this instruction. You want to enter the critical section and execute this entry section code, which starts with this machine instruction. You execute this machine instruction. As a side effect, it sets the lock value again to 1. So it was 1. You reset it to 1. Is there a problem with that? No, right? The lock value was 1 and you are setting it to 1 again, no problem. And then you are comparing now, the register will be what now? Will be 1 or 0? 1, right? So you compare register value with 0. Are they equal? No. Jump not equal to where? That statement here, that point in the code. So that means you again do the same thing. So you loop to lock. You take the lock to a register value, which will be 1. During this time you set it, and compare it against 0. If it's not equal, you again loop around. Okay? That means if the lock was set by somebody else, that means somebody else is in the critical region. Then you will see the lock value and register value always 1, and you will loop around here. Okay? In this way, you are prevented to enter the critical region, from entering the critical region. Is it clear? So this solution will allow only one process to be entering the critical region. And there is no danger here that, for example, assume, for example, you execute this machine instruction. Assume the lock was 0, nobody in the critical section, that you would like to enter the critical section. There are two processes that would like to enter the critical section at the same time. One of them is executing this machine instruction first, right? Since this is an atomic, indivisible machine instruction, only one of them, the execution of that can be sequential, not interleaved. Me or the other process will execute that first. Assume I have been the process that is now executing this one. During this time, I cannot be interrupted. So after I execute this, what will I have? I will have my register, the register value to be loaded from the lock, and lock is set, okay? So now I compare. Before, however, after executing this machine instruction, I can get a interrupt, okay? I can be suspended. The system can suspend me, right? So at that point, I can be suspended and the other process can run, and it will run this machine instruction. It will load lock value to register, and we'll do a comparison. What will it be seen by the other process? 1, right? The other process will see lock value 1 and will not be able to enter the critical section. Even though then, sooner or later, I will be executed again from this point, from where I left off. So I will compare the register value with 0. What was the register value? 0, right? So I will not jump to here and will return and enter the critical section. So that means even though, for example, at this point or there and so on, I get interruption, suspension, it's not causing any problem. Okay? Assuming that this machine instruction is atomic, indivisible. Any questions? But if I would, for example, implemented this machine instruction with 2 assembly languages, like for example, I use a move machine instruction, moving the lock value into register, and then setting the lock value to 1, another move instructions, right? 2 move instructions, or a load and store machine instructions could be used instead of this one. Then I could get a suspension just in the middle. After doing a load, before doing a store, 1, I can get a suspension just in the middle, which may cause a problem. Do you understand? Any questions here? Okay, so of course you will program those in the project. In the next project you will implement some synchronization solutions. So we can stop here and we will continue in the next lecture.